Methods of preparation of alkanes. There are total 7 methods we will be talking about here. And if you remember the list of these methods, it will be easier for you to recall these. Okay, so I suggest that you first memorize the list. First is Sabatier and Sanderson's reduction. The second one is reduction of alkyl halides except fluorides with zinc and dilute HCl. There is some specific point about it I will be talking about. Then Wurtz reaction. Just similar to Wurtz reaction, we have Wurtz fatigue reaction and fatigue reaction also. Although in NCERT they have not included these two, but these are very similar to Wurtz reaction. That's why I have included. Specifically, probably why NCERT has not included these reactions here, because we are talking about only alkanes. But fatigue reaction and Wurtz fatigue reaction, these two are related to aryl compounds as well. So that's why probably NCERT did not talk about it, but I clubbed because these are very similar. The next one is decarboxylation. Decarboxylation, as the name suggests, the carboxyl group goes away. Carboxyl group goes away from the sodium salt of carboxylic acids. So suppose we have CH3COOH acetic acid, sodium salt will be CH3COONA. From this, the carboxyl group will go away. Then the last one, coal-based electrolytic method. The first one, Sabatier and Sanderson's reduction we are talking about, and this is reduction, right? And if you remember reduction, one of the reductions was that if you add hydrogen, that is reduction. So that is what we do here in presence of catalyst, nickel, palladium, platinum, any one can be used here. So we use alkenes. We can use alkynes as well. Okay. So from alkenes or alkynes, when we add hydrogen into it, what will happen? The double bond or triple bond, that is pi bonds, will break and hydrogen will get attached. These are just catalysts. These do not take part in the reaction. Rather, they just increase the rate of the reaction. Another example will be propene. So if you have propene and you get it reacted with hydrogen in presence of platinum, palladium or nickel, you will get propane. So ethene will give you ethane. Propene will give you propane. What will happen? That this bond will break, and when this bond breaks, one hydrogen each from here will get attached to each carbon. Similarly, triple bond. Okay, so propyne, but here because we have triple bond, 2 pi bonds will break. We have 2H2 here. So when one bond breaks, 2 hydrogens get attached, one on each carbon. When another pi bond breaks, another hydrogen gets attached to each carbon. And we again get propane. So remember, whether we use propene or we use propyne, in both cases, the product is same, propane. Similarly, if we use ethene or if we use ethyne, the product will be same. The only difference will be instead of 1 mole of H2, 2 moles of H2 will be used. But all the pi bonds will be broken and hydrogen will get attached. Simple reduction. Another example is vegetable oil. Vegetable oil formula is very complex, right? And depends on which particular oil we are using, whether we are using groundnut oil, sunflower oil, soybean oil. And we are not going into those details. Very complex formula. Even in IIT, it won't be asked. We just say vegetable oil is a mixture of alkanes. And when it is treated with hydrogen at high temperature, 573 Kelvin, we get vanaspati ghee, vegetable ghee. Okay, vanaspati ghee means vegetable ghee. So it is basically artificial ghee, not natural one, artificial ghee. And it is an example of reduction by hydrogen. So that's why under Sabatier and Sanderson's reduction. Next one, reduction of alkyl halides. Remember the previous one, Sabatier and Sanderson's reduction was from alkenes or alkynes. We are talking about preparation methods of alkanes. So obviously in all preparation methods, we will get alkanes. The first one was from alkenes or alkynes. Here again, we are talking about reduction, but in this case, reduction of alkyl halides with zinc and dilute HCl. What happens? First of all, we don't do this for fluorides because the reaction is very violent. We don't have any mechanism, or we would say we don't have any economical way to control the rate of the reaction. So that's why we don't use it for fluorides. We use it for chlorides, bromides, And in case of iodides also, in case of iodide, obviously the reaction is reversible, so that's why we need to do some trick there. But chlorine and bromine very easily. So suppose we have chloride here, we get it reacted again with hydrogen reduction in presence of zinc and HCl. Remember, this H plus comes from HCl. So either you write HCl or you write H plus, it is same thing. Okay, I have written both just to tell you that this H plus comes from HCl being used here. HCl being used. Okay. So what happens here? Again, addition of hydrogen, one hydrogen atom replaces chlorine. So what's happening here? Why we are calling it reduction? Reduction is either addition of hydrogen, that is electropositive element, or removal of electronegative element. So that's what's happening here. Chlorine is going away. Chlorine is getting attached to the remaining hydrogen. H2, one hydrogen gets attached to CH3, produces CH4, and chlorine gets attached to the other hydrogen available. So chlorine is going away, hydrogen is getting attached, both support the definition of reduction. That's reduction. Okay. Now there is something specific which you need to remember, and that will be basically clear when I explain it with bromine example. Here I have propyl bromide. Okay, again the similar thing. Here you have two hydrogens, one hydrogen will get attached here, so you will get propane, and bromine will get attached to other hydrogen, will give you HBr. Now you might have noticed that in first case we are using HCl and we are getting HCl. Sometimes students get confused here, and students have given wrong answer depending on the situation. So you need to be very clear that in this case basically HCl is being used just to provide H plus. Okay, this HCl we are getting from here, similar to this one, this HBr we are getting here. This HCl just provides the H plus. Now sometimes question is asked in this one, why it is useful, more useful to use alkyl halides instead of alkyl chlorides, instead of alkyl bromides. So you can see why it is preferred. It is preferred to use alkyl chloride. The reason is you need very small amount of HCl, because the moment HCl is produced, that HCl will provide H plus. So you just need the smallest amount possible of HCl initially. After that HCl will be produced and the reaction will proceed with greater rate itself. Okay, now different question is asked. The question is asked that during production of alkanes from alkyl halide, reduction of alkyl halide, why the rate of reaction initially is very slow and then it accelerates? The reason is very simple, because initially we don't have HCl, okay, in great amount. It is not available there and there is no need. Okay, but once HCl is produced, it acts as acid to provide H plus, and then reaction accelerates. So that's another type of question which is asked. Okay, but you need to just remember that HCl is for H plus. The halide, hydrogen halide, is produced from this part. Addition of hydrogen, removal of chlorine, addition of hydrogen, removal of bromine. That's why it is reduction. Okay. Now what's reaction? What's reaction is named reaction, very important one, and most probably one question, whether direct or indirect, you will get in your exam. Okay. What's reaction is very simple. It is again from alkyl halide. So the previous one was from alkyl halide. Okay, this one is also from alkyl halide. Okay, but this is not reduction. Here what we are doing, we are taking two molecules, okay, of same alkyl halide. So if we are using methyl bromide, both of these are same. Okay, obviously this is a way to write it so that you can understand it in a better way. Otherwise you can write 2CH3Br plus 2Na, and this is what you will be writing, okay, normally. but here just to make you understand why, how the product is produced. So when you have methyl bromide reacted with sodium metal, okay, what happens? That sodium combines with these bromines, that is halides, and produces NABr, and remaining alkyl groups attach together to give you alkane. So here it should be very much clear that you cannot produce methane from here. You cannot produce propane also from here. I will tell you why. Okay. Methane, obviously it is very clear because the methyl bromide is the lowest alkyl group. You can't have carbon less than 1. So only 1 carbon you have here, and it gives you ethane. So it means methane cannot be produced from here. Now, the point here is that why we can't produce odd numbered alkanes from Wurtz reaction. This is very, very important question which is asked. Okay, so you might think that if I have CH3Br and I have 2Na, and here I take, instead of CH3Br, I take CH3CH2Br, ethyl bromide. So if I take methyl bromide and ethyl bromide, in that case what will happen? And remember, this dry ether is used because it absorbs moisture. Dry ether absorbs moisture present in the air. Otherwise what will happen? This sodium is so reactive to moisture that it will react with the moisture present in the air. To avoid sodium's reaction with moisture, we use dry ether. Dry ether absorbs the moisture. Now you might think that I said bromines will combine to sodium and they will give you 2NABr, and rest of the alkyl groups will combine. You will get CH3, CH2, CH3. Yes, this reaction will happen. Okay, there is no problem into that. But what will happen? That there two other alkyl groups will also combine. So this reaction will also take place. Why? Because you have methyl bromide. Methyl bromide will react with methyl bromide. There are billions of molecules, right? If I have 1 mole, in 1 mole of methyl bromide, there will be 6.022 into 10 power 23 molecules. So many molecules will combine together. So this first reaction will also happen along with the second one. And this will also combine with itself. You have ethyl bromide. So if you have ethyl bromide, 1 molecule of ethyl bromide will react with another molecule of ethyl bromide and sodium. So this reaction will also take place. You will get butane also. So that's why Wurtz reaction is not preferred to produce odd numbered alkanes, carbon alkanes. Anyway, it cannot be used for methane, production of methane. So it cannot be used to prepare methane. And it is not preferred for preparation of odd numbered carbon alkanes, because you will get a mixture of these 3 alkanes. Now the point is, what's the problem? Even if it is mixture, what is the problem? The problem is they have very close boiling point. So boiling points are very close. It means we can't use even fractional distillation to separate them. We can't use even fractional distillation to separate these compounds. So that's why Wurtz reaction cannot be used to prepare odd numbered carbon alkanes. If we have ethyl bromide, then obviously I have already told you butane will be produced. Okay. So this question in Wurtz reaction, what will happen if 2 different alkyl halides are taken? I have already explained. A mixture of 3 alkanes will be produced. A mixture of 3 alkanes will be produced, and it is difficult to separate those alkanes because they have very close boiling points. The condition to use distillation or even fractional distillation is that there should be at least a difference of 20 to 25 degrees Celsius between the boiling points of 2 components, constituents. Wurtz-Fittig reaction. Now it is very much similar to the Wurtz reaction. The only difference is Wurtz represents alkyl halide. So if you remember, I used methyl chloride, ethyl bromide. Okay. So alkyl halide. Fittig part represents aryl halide. Aryl means, for now, just you can consider aromatic compound means benzene compounds. However, there are conditions, not necessarily benzene ring. There can be other compounds as well, which can be aromatic. That's something I will be talking about in other class. So if it is Wurtz-Fittig, it means one halide is alkyl, the other one is aryl. That's it. Okay. So this is alkyl halide, this is aryl halide, and rest of the part is same. You have two NaCl produced and remaining alkyl and aryl will combine, and here you will find toluene to be produced. Right? Now the question is, here also you have different alkyl halides or aryl halides, different halides. So won't we get the mixture of three alkyl or aryl halides? Because this methyl chloride will react with methyl chloride, will produce ethane. This aryl halide will react with this aryl halide, will produce, here in this case, C6H5 biphenyl. It is not called benzene, right? It is called biphenyl. The reason is C6H5 is phenyl group. Okay, so it will produce two benzene rings attached together, not called benzene dibenzene. We will call it diphenyl. Now the question is why we don't bother about that. We don't bother about that because here the difference in boiling point is sufficient. Okay, so in this case we do get a mixture of three alkanes or aryl compounds, but they have sufficiently different boiling points and hence can be separated by distillation. Next one, Fittig reaction. So as I said, Fittig part is aryl. It means here both will be aryl halide. Both are aryl. Here this will be producing Cu2I2. Remember here we are using 2Cu metal. Okay. In aryl case, Fittig reaction, we prefer to use Cu. Remember, we can use Na also. Okay, we can use Na also, but sodium is reactive with the benzene also. So that's why we prefer to use 2Cu. And then rest of the parts will combine, will give you diphenyl. Next, decarboxylation. Decarboxylation means carboxyl group goes away from the sodium salt of acid. Sometimes you might get this reaction written as from the carboxylic acids themselves. So instead of sodium salt of carboxylic acid, it might be written as decarboxylation reaction is the removal of carboxyl group from the carboxylic acid only. The alkanes produced contain one carbon atom less than carboxylic acid. The reason is very simple, because carboxylic group is removed that contains carbon. So if this is removed, we will get one carbon less. This is the reaction. We get the sodium salt of carboxylic acid. Here this is sodium salt of acetic acid. What is acetic acid? CH3COOH. This is acetic acid. If sodium replaces this one, now it is sodium salt of acetic acid. This is sodium salt of acetic acid. When it is reacted with caustic soda in presence of quicklime, it is heated with caustic soda in presence of quicklime. Now this mixture is called soda lime. The reason is this is caustic soda, this is quicklime, so this is known as soda lime. So sometimes you might get it written as that sodium salt of carboxylic acid is reacted with soda lime. Okay, it's heated with soda lime. What we will get? We will get alkane, but this alkane will have one carbon less than the carboxylic acid or sodium salt of carboxylic acid. Here you have 2 carbons. Here you have only 1 carbon because the other one has been removed. The other one is here with sodium carbonate. Okay, so what I am saying here, you need to remember this is soda lime, NaOH is caustic soda, CaO is quicklime. This mixture is used out of which caustic soda reacts with the sodium salt of carboxylic acid. The quicklime acts as catalyst. Another example, instead of ethanoic acid or acetic acid, ethanoic acid, same thing, you can have propanoic acid, sodium salt of propanoic acid. Okay, no, this one is butanoic acid, 4 carbons. Here it is butanoic, not propanoic. Okay, you can have propanoic as well. Here it is butanoic acid, and the result will have 1 carbon less, that is propane. Then Kolbe's electrolytic method, the last one. Okay, here it is very important to know on which particular electrode which gas is produced, on which electrode the alkane is produced. It is very simple question which is asked very frequently, so you must remember on anode what is produced, on cathode what is produced. Okay, that's very simple. I will just tell you that even if you don't remember, you can get the answer in the exam. Okay, the alkanes produced at the anode contain even number of carbon atoms. Again, if you recall, in Wurtz reaction we said that we get even number carbon atoms. Wurtz reaction, even number of carbon atoms. We don't get odd numbered because otherwise we get a mixture of 3. Here there is different reason, right? Here there is different reason why we get only even numbered carbon atom, but here also, here we get even numbered. In Wurtz reaction, we don't prefer to get odd numbered carbon atom. Okay, here we cannot get odd numbered carbon in the alkanes. Okay, that's the difference. So this is the reaction. Overall reaction is this one. Overall, okay. The sodium salt, remember here also I am using sodium salt. In decarboxylation also I use sodium salt of carboxylic acid. Here also sodium salt of carboxylic acid. I am doing electrolysis. Electrolysis is done with water. Okay, so that's why 2s2 written here. I get CH3, CH3. So I have same number of carbon atoms, okay, CH3, CH3, but carbon dioxide is released, hydrogen is released, which makes it very important to know where, on which anode these are released. Now we are trying to understand that with mechanism. The mechanism of Kolbe's electrolytic method is asked separately as 2 marks question. So pay attention here. This is sodium salt getting converted into its ion. So sodium salt in the solution, when you mix it in water, remember we are doing the reaction with water. When it is mixed in water, it gets dissociated into acetate ion and sodium ion, these 2 ions. Then at anode, what happens? At anode, always oxidation takes place. So this is something you should remember. And if you remember these things, you will be able to obtain yourself on which electrode which gas will be produced or what reaction will take place on anode or at cathode. So at anode, it is always oxidation, which you should remember. At cathode, it will be reduction. And you know what is oxidation, what is reduction. Those definitions, I hope you remember. So in this case, what happens here? The acetate ion, this ion, obviously oxidation will take place. And oxidation in terms of electrons is loss of electron. Loss of electrons is oxidation. That is the definition. And sometimes I say to remember loss of electron is oxidation, I say remember the term loxidation. Although there is no such term in dictionary, just coined it to remember loxidation. Loxidation means loss of electron is oxidation. Loss of electron is oxidation. Just memorize it. Now here what happens, the acetate ion loses 2 electrons. So it is loss of electron, oxidation is taking place. And when it loses 2 electrons, there is no charge here. And when there is no charge, it is unstable. Okay, it is unstable here because these 2 electrons have been released. After that, what happens? This produces the methyl free radical and carbon dioxide is released from here. Okay, so what's happening here? And you should remember by the name itself, decarboxylation, COO group is going away. This COO is going away. That is CO2 will be released. So CO2 will be always obtained from where? From this part, not from sodium part. It will always be from the anion, acetate ion here. Okay, so acetate ion will give you carbon dioxide. Okay. And when it gives you carbon dioxide, what happens? This part is released as carbon dioxide, and this CH3 is not alkane. It can exist only as free radical, and free radical obviously is not stable. Stand alone, it is not stable. Okay, so that's why what will happen in next step, these two CH3 will combine. So one CH3 will combine with another CH3. So one CH3 has 1 electron, another CH3 has 1 electron. Remember, I am writing 2 everywhere. Okay, so intentionally I am writing 2 here. The reason is, if I write 2, I will get 2 CH3. It is easier to explain that these 2 CH3, these 2 electrons will join, and I will get CH3, that is ethane. So that is next step, what will happen. So first try to understand at anode what will happen. The acetate ion will lose its 2 electron, and this is just intermediate. Remember, this is just to explain it. Actually, this is what is obtained, and then the methyl free radical combine. Then methyl free radicals combine to form ethane. At cathode what will happen? At cathode, H2O will combine with the electrons released in the previous step. So at anode, if you see, electrons were released here. These 2 electrons released. These 2 electrons will be used at cathode. So at cathode, what will happen here also, I will, instead of this one, I will write it like 2H2O plus 2 electrons will give you 2OH minus plus 2 hydrogen free radicals. So I have multiplied it by 2 just to facilitate the usage of 2 electrons. 2 electrons were released, 2 electrons are being used here. Okay, the hydrogen free radicals will combine. So 2 hydrogen free radicals, they will combine and they will produce hydrogen. So at cathode, hydrogen will be produced. So I'm repeating, you need to remember, at anode, alkane will be produced. At anode, alkane will be produced and carbon dioxide will be produced. At cathode, hydrogen will be released. At cathode, hydrogen will be released. Why? The reason is very simple, because at anode, oxidation will take place. At anode, oxidation will take place. At cathode, reduction will take place. Oxidation is loss of electron and reduction is gaining the electron. So we are gaining the electron, the water molecule gains the electron, so that's why it is reduction. If you remember that in terms of electron, at anode, loss of electron will take place, and loss of electron can be out of these 2. Okay, I'm just going back. Out of these 2, which can lose electron? The one which has extra electrons. So here you have extra electron, this can lose electron. So here this will get oxidized, this will gain electron, right? So that part will lead to the reduction. So at cathode, you have hydrogen free radicals combining and giving you H2. Now the question, why methane cannot be prepared by coal-based electrolytic method? The answer is very simple, because here one methyl free radical combines with another methyl free radical. So the lowest possible alkane is ethane. You cannot produce methane. And this is again the reason that you cannot produce odd numbered alkanes, because the two similar free radicals will combine. After methyl free radical, the other one free radical will be CH3CH2. This is the free radical. So when CH3CH2 will combine with another CH3CH2 free radical, they will produce butane. So after ethane, only butane. You can't produce propane. So that is the reason. In pole-based electrolytic method, alkane is prepared by two alkyl free radicals. That's why. Now the question is, why methane cannot be prepared? This is something I have done right. So methyl free radical combine and give you ethane. It means alkanes produced would have at least 2 carbon atoms. Okay? I also explained that why odd numbered alkanes cannot be produced. The reason is very simple, because two similar alkyl free radicals will combine, and when two similar alkyl free radicals combine, they will always produce even numbered carbon atom alkanes. That completes the preparation methods of alkanes.